Today is October 5th, 2011. This is AP Stats at Berkeley High School. And we're going to finish up, or at least we're going to begin to finish up Chapter 3 by talking about the least squares regression. Whoops, that's interesting. Let's try that again. There we go. So we started this chapter talking about looking at a way of talking about the relationship between two quantitative variables from the same data set. And we'll finish this lecture talking about what the calculator can do for us in terms of more quantification of that relationship. And we're going to do that doing something called the least squares regression. When we're done with this section, you should be able to interpret a regression line. You should be able to calculate the least squares regression line using your calculator. We'll talk about this idea of a residual and how to calculate residuals. We will talk about creating a plot called the residual plot, and we'll have to know how to interpret it as well. We will determine how well a line fits the observed data, and then also, besides being able to do all this on your calculator, I need to be able to you need to be familiar with the output of a couple of different statistical programs and how they compare to what the calculator prints out. So, lots of things to do. We will not be able to complete it all with the time that we have left in today's class, but by the end of tomorrow's class, we should be able to get through all this stuff. All right, so let's talk about this idea of a regression line. When data have a linear relationship, when you have the situation where you look at a scatter plot and you say, I believe that relationship is linear, we may want to try to say, if there is a linear relationship in that data, how can we describe it using an equation? Now, you've been doing equations of lines since way back in your Algebra 1 days. You learned rise over run. You learned y is equal to mx plus b. We are essentially going to do that, not just based on something in the book, but rather based on real data, and then say, if there is a linear relationship, what is the y equal mx plus b relationship? Now, some people make a distinction between math classes and stats classes. In a lot of colleges, statistics is not in the math department. It's in the statistics department. And so some of the vocabulary that we'll use will not cross over. Some of it will, because this happens all the time between different disciplines. A regression line summarizes the relationship between two variables, but only in settings where one of the variable is the explanatory variable and we want to use it to predict the value of the other variable. So we're going to only do this in a situation where we believe that there's an explanatory response relationship between the variables. So our definition, a regression line describes how a response variable y changes with respect to the explanatory variable x. And we often use the regression line to predict values of y for some given x. So for some given, so we're looking at a relationship between explanatory response. We create the regression line because it allows us to say, hey, for this new value of x, what do we think the y is going to be? Okay. So in this example they have on the bottom of the page, hey, there's a scatter plot. And we looked at scatter plots in the last section. We say, if there is a linear relationship, where's that line that best goes through the data? They put it in red. And now that you have this relationship, and this relationship, see, the x-axis, the explanatory variable says non-exercise activity. The y-axis is fat gain. And basically they say, if you do less exercising, the activities are measured in calories. If you burn more calories, there seems to be a lower amount of fat gain. Does that seem reasonable? Does it seem reasonable that your activity level is a predictor of your fat gain? That's reasonable? Okay? And the last part is, hey, for some level of activity, let's say 400, can we predict what the fat gain is going to be? In this case, 2 kilograms. So we have data. We have a line that we'll call, for right now, a line of best fit going through that data. And then we can use that line of best fit to say, what do you predict will happen based on this model? Now, does that mean absolutely that activity level 400 calories will achieve a fat gain of 2 kilograms? No. But it's a reasonable guess. And people need to make reasonable guesses in their lives. You guys are in the middle of course, of a huge reasonable guess. Where are you going to go to school next year? Well, Abby's going to Berkeley High School. But the rest, are you the only junior in the class?
She code.
Okay.
You code too.
Okay. So what reasonable guess are you making?
They can go for it.
No. But what reasonable guess are you making, Jason?
What college I'm going?
Yeah.
I don't even know yet, man.
But the thing is, you got to make a guess, right?
Yeah.
You can't predict perfectly whether you're going to be happy in your choice, can you? But you might as well use data, and you might as well see what a reasonable guess that the data gives you. All right. We do this all the time in our lives. All right. There's another example of an 800 calorie value ends up mapping to something a little bit close, less than 1 kilogram weight gain. All right. So let's talk about the regression model and what it does for us. All right. So a regression line, a lot like the normal distribution, is a model saying if everything's perfect, this is the way it would work. It gives us what's called a compact description, a very small description of summarizing all that data into that model. In fact, for any given line, how many numbers does it take to describe it? 2. Those 2 numbers are? No, x and y are our variables. For any given line, how many numbers does it take to describe that line? 2 numbers. What are those 2 numbers? Slope and intercept is the answer that I was looking for. Okay. This is not going as well as I would like, but we'll try it again. Okay. So, if I have a bunch of data, I want to summarize that data in terms of a linear model. That model is going to look like, at least on paper, the way you write it on your paper, this thing called y hat is equal to a plus bx. Wait, I thought you said we summarize lines using slope and intercept. I we would use what we had in Algebra 1, mx plus b. But I'm writing this thing here that says y hat equals a plus bx. It's the same thing with different letters. It's the same thing with different letters. This b is equivalent to that a. It's some constant without a multiplier. The m, the coefficient on x, matches up to that letter b. Alright? So, different letters with those same ideas. Okay, let's talk about what's going on in the equation. First of all, y hat. Why do we need to put a hat onto y? Because it's cold. Okay, because it's predicted. That's actually a great answer. So let's go through the difference. When I have a data set, I've got a bunch of x values. I've got a bunch of y values. Alright? And when I talk about a y value, I am going to always refer to what I'll call a real y value, a real data point, a real thing that has that value. I create this model. In this model, we're not creating real data, so I can't use the letter y anymore. So I need a new thing. It kind of acts like a y, but it's not a real y. We call it a predicted y. And so we use the hat. We take the letter y and we put a hat on it. And so now you can make a distinction between a real data value y and a predicted data value y. So y hat. Okay, b is the coefficient on the x term. And we've known from Algebra 1 that that number, the coefficient on the x term, is the slope of the line. And then a is the y-intercept. It used to be what you used to call b. All right? So y hat is equal to a plus bx. Can you get used to this new way of writing a line? You're going to have to. Welcome to stats. Okay, now, the reason why it's written that way as compared to your standard mx plus b is because although we're only going to be looking at linear relationships in this chapter, the relationships aren't necessarily always linear. Perhaps the relationship is quadratic. Well, this form of the answer allows us to easily make it a quadratic by adding another coefficient and another x term, but this one's squared. Maybe the relationship is cubic, in which case we add another coefficient and we add another x term. This particular standard of writing it allows us to expand the kind of model that we use easily, so the statisticians like this particular form. And that's why it's written that way. All right. Can I go on to the next slide? All right. So, consider the regression line from the example, does fidgeting make you slim? Okay. Two things. Can we identify the slope? Can we identify the y-intercept? And can we interpret them? Interpret them. Let's attack those two problems. So here's our regression line. From the regression line we can figure out what the slope is. Can we take 2 points just like in algebra class? Answer, yes we can. All right? How about there's this point right here. It says A is 3.505. So one point is the coordinate pair 0, 3.505. Is there another pair of values that we can use?
What's up with that minus there? Is that like
Right here?
Yeah.
Oh, that's because that's the x value 0. It goes a little bit into the negative territory. They're just making that.
Is that always gonna be like that, or is that just like for the sake of the example?
For the, if the x values have both positive and negative values, we tend to draw that axis in.
Can you burn negative calories? Because, wait, mine's at negative 200 calories. I want to burn positive.
You eat more than you work out. You're eating so much, so like you're burning calories, because you're chopping your.
But it doesn't say. So yeah. So if your activity is eating, I guess.
Competitive eating.
It does seem like a bit of a stretch. Hey, can we find another pair of points?
Yeah.
How about this one here? It's right on the line. Well, that looks it weigh about 700. And one. So there's two coordinates. Can we find the slope of that? I think we can. I think we find the slope by saying 3.505 minus 1 divided by 0 minus 700. I would really like someone on a calculator to do that for me, please. Negative 0.004. Now, we probably won't get to the interpret the A stuff, but what does that mean?
It's a negative association.
It's negative association, that's why the negative sign. But here's what every single question where they ask you to interpret the slope, it always has the same general form of answer. For an increase of 1 in calories of non-exercise activity, for an increase of 1 in the x scale, in this case there is a decrease of 0.004 in the y variable, fat gain. For an increase of 1 in the x, there's this change in y. That same formulaic answer. So can you always remember for any question like interpret the slope? Start, you say, I got this form. For an increase of 1 in x, and then say what the x is. Non-exercise activity. There is then look at the sign of the slope. If it's negative, you say decrease. If it's positive, you say increase of, then say the number, 0.004, in, then say the y variable. Very formulaic answer. All right. How much time do I have left? I saw Paul putting this stuff away. I got 10 minutes.
I was just going grumpy with myself.
Oh, okay. Let's see what the book has to say for all of this. Here we go. I thought I said clear drawing. Clear drawing. Oh, I hit the restore right. That's the problem. All right. So there is their regression equation. And again, let's say what they say about the slope. The slope says for the amount of fat gain predicted to go down by this amount for each calorie added. I think we said exactly the same thing, but in a different order. We said for each calorie added, so much extra weight gain. And what is the y-intercept? If we had 0 calories in non-exercise activity, we would be at the y-intercept value for weight gain. Okay, so the interpreter is always these basic formulaic answers. prediction. What if someone had exactly 400 calories? How would we find out what the predicted weight gain would be? Now, doing it just by eye, you go up and we go over and we say about 2. But since we have a regression equation, we have the ability to plop the values in and then run it through the model. We'll take the value 400. We'll put it in the non-exercise activity variable, and then we'll find out what fat gain hat is. Yeah, it sounds funny to me too, fat gain hat. Okay, and so the predicted amount of fat gain hat, sorry, that's for being redundant. If I say hat, it's already a predicted value. The predicted fat gain is 2.13 kilograms. Good news, bad news?
Good.
Congratulations, you are Eagle. My wife went to Eastern, but she was not an Eagle. They used to be, their mascots used to be the Huron. The Huron, it's a tribe of Indians, oh sorry, Native Americans. But someone complained and said it was culturally insensitive, and so after she left Eastern, they changed the mascot from the Eastern Michigan Hurons to the Eastern Michigan Eagles. Chippewas don't care.
Yeah, evidently not really a tribe anymore or something.
I don't know. Your question? No? Okay. All right. All right. Now, some warnings about using these models. The idea of doing a predictive, using these models to get a predictive value is very powerful. But the idea of using these models to predict values that are way out beyond the data is called extrapolation. And extrapolation is dangerous. Let me give you an example of how it would be nonsensical to extrapolate. I'm going to do a linear relationship. Back in, I believe, the 1960s, I think it was like 1967, British runner named Roger Bannister was the first person to run a mile in under four minutes. Okay. Now, since the late 60s, though, the time for the 1 mile distance the records have gotten broken and broken again. The record times are low, well underneath 4 minutes. Now, if we take this line and continue this trend, the obvious conclusion is sometime in the 22nd century, it will take 0 seconds to run 1 mile. That makes sense. What's that?
Yeah, I'm almost there. I'm at 32.
Do that fast?
Yeah, I'm at 32 seconds.
32 seconds. So the data is way down here, and going way beyond the data and trying to predict the time outside the data is called extrapolation. It's a dangerous thing to do because you get nonsensical answers.
Wait, it means trying to predict.
It's trying to predict using the linear model way beyond the data.
Okay.
The data is in one thing, and when we go way, way out, we get another answer. And the answer, when we're way beyond the data, is not a particularly good prediction. All right. So,
Mr. Fedor, what's a good mile time?
what's a good mile time? For what distance?
Mile.
Oh, okay. So if you're running exactly 1 mile, record times I think about
No,
3.
like what's like a good mile time? Not record.
Oh, okay.
I was like, I guess 550.
550 is, I mean, to be competitive at the high school level, that's kind of high. Well, high 4 minutes. 4:30 to 4:45, I think would be a competitive time. I think. No. But I mean, if you're running a marathon, top marathoners run at a pace that are a little over 5 minute miles. All right. So this will be our last slide as I feel your guys' attention waning away. So our official definition: extrapolation is the use of a regression line for predictions that are far outside the intervals of values that were given. Such predictions are not accurate. By the way, another classic example of this happening, a few years ago, the Tigers had a first baseman named Chris Shelton. And Chris Shelton started the season on an absolute tear. I think he hit 10 home runs in the first 20 games. So one of the things that you could do is say, based on the number of games he played, you could extrapolate out and say, how many home runs is he projected to hit? And I think his projection to hit number was something like 125 home runs that season. And then by the end of the season, indeed, he was in the minor leagues because they figured out he couldn't hit a curveball. No, he isn't. So anyway, so extrapolation is dangerous. We are on slide 8. On slide 8, we'll start tomorrow. We'll finish this up tomorrow. All right, I'm done. Woo. Jazz hands.